Tropical and subtropical regions around the world have ideal conditions for growing the moringa tree, a miracle plant known for its nutritious leaves. What is less known about this miracle tree is the high-value oil one can extract from its seeds after they have been shelled and pressed. The moringa seed oil can be used for cooking, for biodiesel production, and its most sought-after application, as a revitalizing oil in cosmetics and skincare products. Typical oil extracting machines are beyond the financial reach of many subsistence farmers. What if we could design a simple machine to help these farmers to capture more value from the trees they're already growing?
Since January 2012, I have worked on designing a set of simple by about 50%. So let's look at this first step in more detail. To facilitate the shelling process, we've been working on a human-powered machine that makes it possible for a farmer to remove the shells with very little effort. This treadle-powered machine tumbles the seeds with hardened objects, in this case bolts, which crack the hard shell from the soft seed. The broken shells fall through the holes in the drum, but the seeds and hardware stay inside. In about 6 minutes, 2 kilograms of moringa seeds can be completely shelled. After shelling, the drum is opened to get the seeds out. The collector here gathers most of the debris while shelling for easy cleanup, and also gathers the shelled seeds once they're done. So the process starts here. The person operating the machine uses the treadle to pull this bike chain. The treadle is pinned on one end instead of being free rotating, so your foot can rest while using the device. In being treadle powered, our device is much smaller compared to common pedal powered devices. The chain coming from the treadle wraps around and pulls a freewheeling sprocket, and is finally attached to the spring here. The sprocket is attached to the drum, which is rigidly connected to the axle and paddles inside. The axle of the drum runs through pillow block bearings on either side. When the treadle is pushed down, the sprocket turns the drum clockwise, and when it is released, the sprocket freewheels back to its original place, allowing the user to continuously turn the drum by simply tapping their foot. The drum itself has some interesting details. The holes all around the drum are large enough to allow the broken shells to fall through, but small enough to keep the whole seeds and the hardware inside while shelling. When the shelling is finished, the door is opened, and here you can see there's yet another mesh. The holes of the mesh are large enough to allow the shell seeds to fall through, but small enough to keep the large hardware inside for the next round of shelling.
Prototyping the machine has proven to be invaluable for understanding what to keep and what to improve. The most important constraint of the system, rotational speed, has driven many of the design decisions. In order to experiment best, the team used a multi-speed sprocket to compare how each size performed. The smallest sprocket spun the drum too quickly, which caused the shells to stick on the sides of the drum. The largest sprocket spun the drum too slowly. The shelling was just as good, but the throughput was too low. The medium size, an 18-tooth sprocket, achieved a happy medium, tumbling the seeds at 2 revolutions per second. As they experimented more with the tumbling, they realized that paddles would agitate the tumbling of the bolts and seeds, speeding up the shelling process. As with many appropriate technologies, the machine is made out of parts that can be found locally. This ensures that the machine's users are familiar with the look and feel of the machine before they've even used it. The use of bike parts as the precision elements of the machine demystifies its use and maintenance.